Hello, today we are going to talk about temperature advection and how we can use the expression for material derivative to find the rate of change of temperature above some point in space. Let's assume we want to find how the temperature changes at the tip of my finger. In today's video, we will learn that if we know the temperature gradient everywhere in space and how the wind blows, we can combine these two information to find how the temperature will change over time at the tip of my finger. Instead of tip of my finger in this room, we will use real atmosphere outside and large scales of motion, but the concept is the same. To spice the problem up, we will also add the radiation, which means, let's say there is some source of light, and in our case that would be sun outside, that is heating tip of my finger, how that would change the temperature over time if, let's say, there is no wind or there is no change of temperature in space at all, but just heating. So we have these three concepts: radiative heating, gradient of temperature in space, and wind. And believe it or not, we only need expression for material derivative that we derived a few videos ago to solve this problem. So I highly recommend you check that video, link is in the description. In addition to material derivative, that video describes Eulerian and Lagrangian description of the flow. So let's set up the problem and then solve it. Here is the setup of our problem. The goal is to find the temperature change in m over 1 hour. We see that spatially temperature is changing for 5 degrees Celsius in the direction of north, which is my y-axis, and this change of 5 degrees is over 100 kilometers. X direction is positive eastward. We also see there is wind blowing at 15 meters per second from north-northeast direction. In addition, we have heating of air at the rate of 1.5 degrees Celsius per hour. What will be the change in temperature in m over 1 hour? To find that, let's first identify what is the angle of this north-northeast wind direction. And we know that north wind would be 0 degrees if this is north. So north would be 0 degrees, northeast would be 45 degrees, so north-northeast is in between, which is 22.5 degrees. Which means this angle, let's call it alpha, is 22.5 degrees. Okay, so we quantified north-northeast direction. Now, to find the temperature change here in m, we just need to use material derivative that we derived a few videos ago. dt over dt is equal delta t over delta t plus v dot nabla t, where t is temperature, small t is time, v is wind, and nabla or del is differential operator. From here, because we are interested in rate of change of temperature in m, we see that delta t over delta t, which is local derivative or local change of temperature, is equal dt minus v dot nabla t. So just rearranging this equation. Or I can say further, delta t over delta t is equal
dt minus. Now I need to write this in terms of components, which is u delta t delta x minus v delta t delta y and minus w delta t delta z. Now we are not given w, there is no vertical component of wind, so this term disappears. In addition, please notice that delta t over delta x is 0. There is no change of temperature in the x direction. The only gradient is in the y direction. So while we have u component of the wind, if we decompose this v vector, there is no delta t delta x, and therefore this term is also 0. So here we end up with dt minus v delta t delta y. And in terms of concept, this problem is already solved because dt is 1.5 degrees Celsius per hour. Delta t delta y is 5 degrees Celsius over 100 kilometers, and v we can find from this vector knowing the angle alpha. So let's plug in numbers. Delta t over delta t is equal dt 1.5 degrees Celsius over hour minus, what is v? Well, you can see that this northern component is simply intensity of v times cosine of this angle alpha and times delta t delta y. But what is delta t delta y? Well, it is 0 degrees Celsius minus 5 degrees Celsius, so change of temperature over 100 kilometers distance. And this is further equal. Let's transform kilometers and hours into meters and seconds respectively. So we get here 1.5 degrees Celsius over 1 hour is 3,600 seconds minus, but look, notice that v component is going in the opposite direction of positive y. So here I will have minus 15 times cosine of 22.5 degrees times 0 minus 5 is minus 5 degrees Celsius divided by 100 kilometers, which is 100,000 meters. If we take a calculator and calculate this, we will get that delta t over delta t is equal minus 0.000276 degrees Celsius per second. But we need to find change in 1 hour. So if we multiply this by 3,600, that will be equal to minus 0.99 degrees Celsius per hour, which is basically 1 degrees Celsius per hour. So we see that in this particular problem, we have positive rate of change due to heating and negative rate of change due to the advection of cold air from north. And in our problem, there will be decrease of temperature for 1 degree Celsius over hour, which means that the cold advection is overpowering radiative heating.
We saw here how these two terms are fighting each other, and in this particular case, advection won, and therefore we have overall decrease of temperature with time. And this concept can be easily demonstrated if we have a lighter and just lungs, and I believe most of you do have these things. If I ignite this and I put tip of my finger over here, I can feel the heat from this flame, and that can be to some extent substitute for this heating that we have here. But at the same time, if I start blowing air, I actually reduce the rate of warming of my finger because I'm advecting cold air from my lungs. And depending, how strongly I can produce this wind, or how strong is the heating, depends how the temperature will change at the tip of my finger, which was exactly, if you think about it, what we had in this problem over here. So you can see that this concept of material derivative can be applied to many, many different situations in real life, from hundreds of kilometers scales of motion to, centimeters and millimeters like here. Until next video, goodbye.